Good morning, everyone. Welcome to the KRVIA Encounters. Today we have Jaideep and Varun as our speakers. Jaideep Mulye has been involved in architectural practice for more than 5 years through architecture, interior, urban, and structural design. His recent work lies at the intersection of architecture, parametric design, and structural engineering. As a design sadhak, he shall be sharing some lively explorations in the making of things of mildly thrilling elaborations about collaborative, parametric, and integrated processes. On the other hand, we have Varun, who is a student of Masters of Architecture and Masters of Landscape Architecture at the Ohio State University. He has been researching techniques for conservation of Native American mounds with Professor Justin Parsher. He has also been teaching assistant for the past 1.5 years of the course titled Outlines of Built Environments. He will be talking about object ecologies. It aims to examine what it means to be an object and in process decontextualize these others to generate a more inclusive discourse on built form. We welcome you, Varun and Jaideep. You could start with the presentation. Thank you.
Thank you so much.
Hi, thank you, Janvi. Hi, thank you, Janvi, for the lovely introduction. So, object ecologies. Um, yeah. So, the idea of object ecologies sort of begins with the standard Indian prasad that is cooked at my house. And as you can see, it has like a lot of components which kind of hold their own, but they are also able to work as a team with other objects on the plate. The objects are uh, the the eater of the plate is not a concern for these objects, in a way that a child or an adult both can eat the plate, but the scale of the human eating them is not a concern. But they are very autonomous in themselves and they are extremely complex by themselves. Um, and of course, there is no hierarchy in these objects. You can club them however you want. You eat them in absurd quantities as you like them. So their consumption is not sort of limited to what you do, and they are not defined by their relations to other objects. Their individual complexity is acknowledged and it is more often celebrated. Um, which takes me to to one of the bigger projects that I did at the Bus Ride Design Studio, um, where we kind of assembled this a set of these large objects that were sort of put into this mill. And what was relevant kind of for my for the discourse that I'm building, to take away from the project, that was that you take a note of each and every object in the project. These objects are either sightless and fixed, like a dome or a Ferris wheel or an amphitheater, which are objects that are kind of on their own, but they can also move around. They can go to other sites if they like, and objects that are somewhat specific, like a John Haydock kind of installation that we did, which was the large HVAC holder, and the flexible sort of uh, skeleton that we had, which held some artistic follies. And they were site specific, but then they were extremely flexible to what they could become. So in a sense, these objects have always remained autonomous. And you can see that the project was in a sense a collection of these objects, and they were pretty much on their own. Um, they could become what they like to become. Um, and they were at different scales and at different details and resolutions. There were small objects which were extremely detailed, so that's what gave them their relevance. And then there were extremely large objects, which you can see on the left, which gained relevance by their sheer scale and probably the graphic that would eventually come on them. Um, we did another project at Bus Ride, which was these high performing individuals, which were these parametric objects, which were inclined to perform and to create these and to have like multiple applications. We eventually ended up sort of building a coral reef and an ecology of these objects, where they could become lighting fixtures on the roof of a cafe. But because they were so highly performative, they could become anything at any scale. For example, the complex one on the right on your screen is designed to dissipate heat very quickly. So it could become anything from an ice tray to a facade of a building. So the scale is sort of flexible for these objects. But what's important is how these objects can land on the ground. So that was kind of step 2 to this project, where I was exploring landing as a phenomena. And I was doing a project with Jeff Kipnis about exploring these definitive architectural objects. And in the course, we were kind of exploring how objects behave. And in a sense, I was exploring how monoliths can exist and how they sit in the landscape. And you can see that there is a sort of jarring relationship with the landscape, that these objects sort of undermine the landscape already. So this is the final thesis that I did at KRVIA. And you can see that objects are gaining complexity depending on their history and sort of borrowing from their history. Now, also, I'm using the word object very loosely when it comes to things that are at various scales, because essentially these are things that sit on their own, which are not dependent on the relationships, as I have sort of described before. So these objects sort of gained complexity over time. But what was also a relevant takeaway from the project was how these objects sit on the ground. And in a sense, they convert the ground into a very significant complex entity, which becomes an object in itself. You can see that there is this large graphic that goes across the ground, and which allows these objects to sit in a configuration and almost move in certain configurations that if they change in the future, they can sort of move around. So they have their autonomy, they have their entity to be themselves. Which gets us to the idea of stuffing. At what if this ground is taken and folded onto these objects to cover them or to inhabit, so these objects kind of become these organs inside the bigger object. So then how does a folded ground become an object in itself? It gains texture, it gains materiality, it gains complexity. It responds to land, it responds to geography. It has objects sitting on it to acknowledge its presence as a new ground that is created. And there are objects that are stuffed into it, which are sort of loosely assembled. And the looseness of assembly is what gives these objects their presence. And the route of movement, which here is described in the dotted line, can show you that you almost move around these objects at every point in time. So you kind of, they always make sure that they are seen as beings, even when you travel through the building, and even when you travel from within them. They create these atmospheric effects that are autonomous to them, but they also work in collective, as you can see on the right. So in this particular project, this was a museum of myths, where a rock had sort of erupted from the ground and sort of created this space by hollowing out. The spikes on the roof were designed to perform in a way that because this was placed in a desert, water was a very important resource. So they were designed to harvest water from the air at dew point, because at dew point, water reaches a certain level of saturation in the air so that it can sort of settle on surfaces. So they were designed to allow water to settle on them and to collect it and to throw it within the building like mist, which sort of cools it down, but also creates this almost surreal atmospheric effect, which is almost mystical, and hence it goes with the whole museum of myth idea that the project was. And it gets me to the next project, which continues this idea of stuffing, where it goes from stuffing to birthing objects, where we took plans from Mises projects, and we were doing a large tower in Chicago. And these plans were then folded and operated upon. These idea of operation for birthing is also kind of seen through the projects. We were operating upon them to create these objects that were then uh, pushed into this facade. And the facade itself was designed to be an object in itself that was folded upon the building. And so it gained complexity by this shifting of grids that were laid on it. And when you see how the facade kind of starts to touch the ground or to be almost independent and free on the top, it makes it very visible that it is an object in itself. It is not dependent on what's stuffed within it. And then it was juxtaposed with other things in the context, obviously by its presence in the context, which sort of draws that jarring difference between the building and the context, and which again highlights the idea of tight fits and loose fits. They are sort of tightly fit on one side and loosely fit on the other, and that is purely the product of the operation that is performed. This leads to absurd programs that are created, various kinds of rooms in the hotel, which were designed for a completely different clientele from what a traditional high-end hotel would imagine. So it almost became like an urban scape in itself, which was where you can almost see that you have public plazas and spaces that are stacked on one on top of the other. The sizes of room are of such varying degrees that there is a variety of people who can afford this hotel, and hence they can sort of you can expect a entire urban spectrum to inhabit them. And which gets me to the difference between my work at Bus Ride that I presented and the work that I have taken ahead from there. The work there, primarily what I took from there, obviously what I'm saying is not their entire pedagogy, but what I'm saying is just a part of their discourse that I'm borrowing to kind of take ahead. And I had those inclinations from my time at KRVIA, which I kind of used in practice at Bus Ride, and then sort of moved ahead into my master's, and it helped me in my master's. So for Bus Ride, it is more of a Manchow soup, where and that's how Zamir describes it. That they are sort of dumplings and complex objects that are within a soup, and which depends very much on the eater, that you need that spoon to eat it. While the discourse that sort of I'm talking about is kind of different from that in a way that it is not dependent on the viewer's perception. And that is where it makes the jump from architecture to landscape, because it becomes from objects to object ecology. Because in an ecology, plants or trees are not concerned with the scale or being of other objects that sort of attack them or sort of inhabit them. The tree does not design itself for a nest. The nest kind of adapts to it and then becomes an object in itself for other objects to sit within a nest. So here is kind of the definition of objects in terms of the whole thing that has evolved through time. So it is neither a sum of its parts nor a product of its relationships. It is a whole in itself, like Russian dolls that kind of sit one inside the other endlessly. So it can almost go down to the level of a detail and still go up to the level of an urban scape. So the idea of an object is not limited to its scale. It's not, and so it is kind of infinitely expandable, and yeah. Objects can kind of nest one within the other, which gets me to this project, which was a carpentry institute that we did in the semester before last, where we took where we took a large cube and we sort of broke it down into pieces, into joineries. So the idea of detail was kind of taken from the level of a mass, and kind of mass was seen as a detail and a method of assembling a building. So the method of assembly of a building was completely different. For example, like this is one of the models from our project, and as you can see, every piece has a high level of complexity in itself, and but can still sit together with kind of other pieces. And each part was very complex, but they were kind of jammed into one another, and they became each piece became a program in itself, and so they were incomplete wholes in themselves. So they also could become a part of a larger landscape and a cityscape because of being incomplete and complete at the same time. Um, and then details were also, then we sort of flipped the scale by making details feel like masses. So a staircase was sort of assembled and then jammed into a larger piece, which led to a creation of a new ground that was essential. So the idea of ground becomes divorced from the idea of just a building coming and sitting on the context, where the ground itself becomes pieces that are assembled and folded to become an assembly in itself that inhabits these objects which sit on top of them. And that is where I sort of took it into landscape architecture. This is one of the earlier projects at Bus Ride Design Studio, where we kind of had these tiny follies that were spread across the landscape, and they were meant to be educational, collaborative objects which kind of encouraged these activities, but they were primarily very autonomous. As you can see them, they were designed to be like circles, they were designed as monoliths, they were designed as these tiny wafer thin fragments that sit on top of the landscape. And as you can see, they were sort of organized like follies. Um, but when I decided to do an urban scape, which was for Columbus Fairground in Columbus, Ohio, I decided to kind of make it free of scale, and so each sort of thread, each sort of line embraces the complexity that is inherent in an urban scape. And that complexity turns into these landscape objects, or these landscape features that kind of have their own being, their own ontology. Um, so the primary sort of tools to configure these landscapes were lakes, mounds, rocks. And you don't see rocks at that scale. Rocks are seen at the scale of a roof that sort of sits onto a building. So it's a kind of a metaphorical rock. But the idea of lakes and mounds is very conducive to this object discourse, because lakes and mounds rarely have a scale to them. You cannot gauge the scale of a large lake or a meandering lake, or a burrow, or a mound. So and landscape lends itself to an object ecology really well, because landscape does what it wants to do. It does not complexity and embracing the complexity comes very naturally to landscape. Like, for example, Acer saccharinum, which is a tree, it sort of takes water from the lake and sort of pushes it up the ground, and it does all this seamlessly while existing in itself. And when and like nature is always loose fit, nobody decides to make a joinery out of 4 trees and 3 rocks and to kind of assemble them in some efficient kind of a way. And when sort of humans try to make intersections or interventions into this nature, it has to sit lightly on it. There is no choice, because the line always looks jarring in nature. And as you can see that the planning and the man-made sort of ideas on this landscape are also seen in a similar way through object ecologies, that you create these seams between, as you can see, like the promenade sort of ends up becoming a stage for things to happen, and this creates a seam between two or three ideas. This creates layering of space, and these seams between the layers kind of start to become the spaces where culture is inhabited. And uh, and yeah, so you see the proliferation of culture in this place, and it's primarily a process of object ecologies has primarily been a process of letting go and embracing the objectness and respecting the objects that they are, for from interiors all the way to landscapes and urbanism. Thank you.
Sure. Thanks so much for that, Varun. That was a very eloquent presentation. I'm Jaideep. I'm currently working at Manjunath and Company, which is a structural consultancy in Bangalore. Am I audible?
Yes, you are.
Oh, fantastic. Thanks. So I'll be dragging you guys to the other end of the spectrum now. What Varun showed was highly conceptual and metaphors and the architecture kind of work which we do. So with my current job description, I'm working at the intersection of parametric and computational work and a little bit of course, a whole lot of structural engineering and architecture. So allow me to second. Yes, sure. Is my screen visible to everyone? Okay. So I worked in different kinds of fields before ending up at a structural consultancy. So there was a bit of architecture, a bit of interiors, and a bit of urban design, a bit of furniture making. And the synthesis I'm going to be talking about is actually that of collaborations, of actually multidisciplinary collaborations, which belong to say engineering and architecture, uh, which in a sense are required to support each other but kind of exist independently as well. So most of my presentation will be dominated by workflows. For college students who are listening in, workflows is a more disciplined, target-oriented elder brother of process, which we all dearly enjoy. But then this becomes a more goal-oriented manner of achieving the design goals that we have set for ourselves. So the process or the workflow that we are familiar with is in college is architectural concepts moving to design development, moving to architectural drawing. And then this continues for smaller projects where a structural engineer comes in and gives his input during the design development phase that becomes the structural analysis and leads to structural drawings, which lead to the last three phases, which are predominantly existing where you will be fabricating elements. It doesn't really exist for a concrete or an RCC construction. But if you are working with wood or steel or the things that need to be put together, the last three blocks of the flow chart come into picture. So if you consider this as a typical workflow, of course, there are other more components of it, like an MEP or other consultants who may be coming in. What I have experienced on a first-hand basis is a more collaborative workflow, where rather than just providing inputs, the structural concepts also start becoming relevant along with the architectural concepts, and this diagram could be considered a generalized explanation, but it conveys more of a studio-based collaboration, because there could be collaborations with masons, with other artisans and craftsmen, and that becomes a whole new workflow by itself. But this could generally convey what a studio-based workflow would be like. So the significant change that happens over here is that structural concepts and structural input start come at the same level of architectural concepts. So that means that other consultants also have more authorship for the project, which means they give more input and bring their concerns to the forefront also, which is a fantastic situation because that leads to a much richer product in the end. Uh, So then the synthesis which I'm going to be talking about today is this trio of architectural, structural engineering, and parametric design, which comes together very interestingly in building systems. Of course, everybody does their own thing, but because of all the inputs together and all concerns getting streamlined, it leads to very interesting building systems as such. Uh, my work in this has been the work which I'm showing today is mostly parametric, is on all of it is parametric design work, and that starts playing an interesting role because architecture and architects work in a more visual based medium, where we work with drawings, models, renders, and structural engineering doesn't necessarily work with that. It works more with with non-visual components, which are more of numbers and formulae and things like that. So when you start visualizing structural logic and start adapting it to architectural concerns, there creates a gray area, or I would say an overlap, where the manifestation of both the inputs starts creating certain visuals, and that starts giving feedback to both the disciplines to evolve further. So that is where my role lies in the projects which I'm going to be showing you today. So of course, there are a lot of options which are available for working in a parametric way. There is also BIM softwares which come in, but I have been predominantly working with Grasshopper, which those who are not familiar is a scripting language. So it is programming, but it is mainly visual scripting. So there is a canvas, as you can see, and you have these components where you given data, which helps you manipulation of geometry and data in its most primal form. But there are certain advantages that come in over here. So one of the thing is that it's a logic based thing. So of course it takes away the freedom that you would begin with a freehand sketch or charcoal sketches or the process that we are familiar in architecture. So there is a certain amount of logic required to start off on this. There can't be a free exploration that we are familiar with. But then the logic starts getting based in the multiplicity, repetition, customization, and it starts to help you build things if you have a seed of logic in place. Uh, the second part is the flexibility and the history. So the interesting part about a workflow like this is that, say, if you're modeling, or let's say you're modeling a cube in Rhino, where you would draw a square and then you would extrude it, and then that would create a 3D solid object from two lines. So what this process would do is that it starts showing you the whole history that you've done. That you have to draw a line, you have to extrude it, you have to cap it, and then make a solid. So that leads to a very interesting configuration because you can see all the steps that you will take for the end product right in front of you. And that allows for almost a surgical kind of a working on this, where you can remove certain parts of the script and feed in different parts to get in a different product at the end. It also leads to a lot of flexibility because you can tap in at step 3 and change it to step 5. You can create variations based on steps you've created now and then branch off into 2 or 3 outputs, which leads to a lot of iterations and a lot of simulations, which can be really, really helpful as architecture starts moving quickly. Third is there is interdiscipline integration, which of course there are, as you may be aware, there are more plugins that also allow engineers to plug into a flow. So basically a flow which may have started by architects to create a certain form goes right to structural analysis as well. And the fourth one, of course, very, very important is the feedback, which can be visual, which could be numeric, which could be computational. So the visual feedback is something that I'll be talking about. Numeric is something that goes into more into disciplines which deal more with numbers, like engineers, maybe MEP engineers, maybe climate analysts, maybe structural engineers who need numbers to uh, quantify and evaluate if a certain aspect of the design is working or not. So I'll be basically talking about three design workflows that I have worked on. One is solving of a form. So it was generated, a highly conceptual form, which was generated by architects, again using Grasshopper. And how do you provide structure to that? How do you start bringing it closer to a more to reality? And how can you make it more buildable? The second would be structural form finding, where we start working with an architectural idea and architectural intent about what we need to achieve at the end. And then the process of form finding goes out based on structural logic. The third one will be design resolution, where architecture is quite clear and it's put on the paper, but it needs a lot of resolution. So the feedback and the flexibility component aspect of Grasshopper becomes very useful. So this was a dome that we were working with. This was sent to us by the architects, where you can see that it's a dome which is based on this asymmetrical kind of an oval object, and then again it's perforated with organic looking squares. So this of course becomes is a more well-known um, side of Grasshopper, where again you go to Voronoi and start generating random patterns, and then you start giving it more logical sequences where you start filleting the edges. So you generate polygons and then you fillet the edges and then you scale them lesser. And you start getting these patterns which can be 2D, 3D, and can be implemented in to create forms. So the challenge while working in a structural consultancy becomes is that yes, the engineers start providing a structure based on the concepts, where we see an interlace of trusses which is created to support this. So it shows a clear demonstration that yes, these are the punctures which we have, which will be windows, and the parts which are solid will accommodate the structure of it, which will give the depth, and then it will also help with the structural part of it, and also the architectural part of it, where cladding and other things need to be added. So fine till this point, but then how do you start putting something in an object without any references? So this is the code that we generated to do that. So if you see, the architecture code was derived in this part of it, where first a small introduction starts creating the form. And then the detailing goes in, so the code starts evolving. So one of the other advantages becomes is that because you have it right in front of you, it starts augmenting slowly, slowly as the design also becomes more detailed. The second part of it, which is this part. I'm not sure if you can see my cursor, but the big chunks with the gray background and the green start adapting the architectural model to a more structural concern. Because of course, once you start talking about structures, there are fundamental thumb rules that come in to begin with. And then as you traverse more towards buildability, there are certain minimum sizes, margins that you need to maintain. So the second process helped us do that. Like, yes, there are certain lines which are created, and that starts helping this. So the software becomes quite ruthless in terms of its workability, where everything needs to be precise. So as you can see, this first aspect which says micro lines elimination is that the pattern started creating much smaller lines, where you have a 45 line in a dome which goes around 20 meters. So it's very difficult to work with a steel tube which is just 20 long in that scale. So there was a lot of cleaning up that was required to translate this form into something that could be taken to the drawing board in a workable manner. So we decided to tap into the script that the architects themselves had created. So that gave us a very nice seamless workflow that could be generated and saved us on a lot of effort as well. This also leads to a good thing where we can have a back and forth, where in case the architect wants to change something, they can change it in the code, and then we can work down the code and adapt to those changes as they happen in the in the upstream part of it. So this is how the surface gets divided into these polygons, which are generated by these dots in the center. And this is how the next step in the form moves, where all these polygons are converted into smoother objects. And so we decided to branch off at this point that yes, okay, the flowchart allows you to move into certain different directions. So the primary structure would be achieved with the polygons which are put over here. And then the organic part of it, which are the openings, would be dealt later. All of this would be available because it's right there on the code. So then to start achieving, we start adding more layers to it, where you have the initial uh, polygons which are then offset to create depth. So all the rules that come in now come in from the structural engineer, who says that yes, we are going to need trusses which are this wide and this deep. So we start putting in the parametric. We start utilizing the parametric part, which becomes that yes, every line should offset with certain distance, and it should create a certain shape. So we start doing this where it's a three-dimensional tubular truss. So we have the top chords and the bottom chords, and this starts creating the truss under that. Uh, then we come to this part where the structure is achieved, and then we need to achieve the openings in this. So then again, it gets tapped into this code. And so every point needs a little bit of back and forth to check if the logic that you're working with is fitting to the design at hand. So this evolved into more concentric rings and then more primary members which started supporting this up. So that was about adapting a conceptual architectural form to structure. The second part and the third part are of the same project, but they are two different structural systems. So this was an institutional building that we were working with, where this is a school, and it's laid out where a lot of buildings are repeating, or at least the building language is repeating. The motif of the roof continues in same parts, and so as you can see, there is a lot of flexibility in the most basic sense, that you have one form which is stretched, which is elongated and scaled to achieve this kind of a thing, where again a parametric component helps because then you don't need to start everything from scratch. So the architectural intent that we had to support as structural consultants was that you have a large roof expanse which is shielding small buildings. Secondly, there's continuity where as you would have seen in the master plan, that all of those buildings are connected internally, and there is a continuity that needs to be taken care of, and also the structural seamlessness needs to happen in this instance. And very importantly, the scale under the roof needs to be snug. So this starts informing structural sizes and the elements that you start using. So of course, we have the structural master plan right here, where you can see all the filigree of these parasols, and the roof continues all through. And then you have smaller buildings which are tucked underneath it. This also works as an independent structural system, where you have the roof as one component and the superstructure and the substructure get treated together. So this is the structural form finding exercise that we did for the roofscape. So the roof in the most conceptual stage becomes, yes, that there is a parasol which is designed, which is a module which is supported at the center, and then cantilevers outside, where the cantilever then supports shelters smaller buildings within to safeguard them from rain and sunlight and provide protection from natural elements essentially. So you have this thing which gets staggered as per the architectural layout. And then as we saw that the continuity was supposed to be achieved. But then how do you fill these gaps? So you get these 13 cases which are going to have the same structural logic, which we know are going to be resting on the parasols over here. But how do you start figuring it out? So then, of course, so the interesting part was that the formal intent is established, and the design evolution happens more with the structural consultant than the space designer. So the architects start giving in feedback, but most of the work gets done because it's a predominantly structural engineering scope. So the primary concerns that we start with is that it has to be lightweight, because of course it is resting on on a structural module which is already cantilevered and supporting that, so that needs to take all the load to the ground. So it needs to be as lightweight as possible, and it needs to deal with extremely large spans. So starting off with this, the evolution process becomes structural form finding, where the workflow goes as modeled, which is done as per structural logic. Then you get a feedback from the architectural team, and the structural visualization also clarifies a few things for the structural engineering team. And then everybody diagnoses and re-strategizes, and then you go back to step one. So this what I'm showing is basically 4 iterations. There were more, but if I were to condense it into a more presentable format, it could be 4 different iterations that we could look at. So the first evolution was the most basic response to that. Yes, that we start lacing the parasols in between and create a simple structure over there. So of course, because with a lot of rigidity is achieved when you start lacing two things like that. So we created troughs at smaller ends where the form went down like this, and then as it moved towards the larger end, it started creating more crests. So the architectural feedback was that the troughs didn't really work for drainage, because all of them would, the whole bay would be drained in this area, and then the other side, the gutter resolution wasn't coming in very well. The second part was that the depth was required for large spans, because we were spanning around 17 meters from end to end into the corners of these parasols which are put over here. So taking this feedback, we moved to the second evolution, which said like, okay, we'll do crests at both ends. So the longer and the shorter end also start becoming arches, and lacing is rarefied in the center because that is not what is required. You can just keep it dense at the end. Then bowstring trusses are introduced so that you get depth for the spans that we want to achieve, and then we curved this edge to reduce the span. So the architectural feedback came like, yes, we cannot put this edge back in because this exposes the buildings to rain and natural elements, and we need to protect it because this is the secondary skin. And a default kind of a surface on which this was created started to make very deformed elements, which would be very difficult to fabricate. So if you can see the second image, where there's a lot of skew which gets generated and the members don't necessarily are, all of them started going into curving forms, which also is not good in terms of structure, because a clean arch would be much better functioning. So third one became where, okay, the lacing was clarified, and the shape of the roof was fine, but it needed more fine tuning. So we introduced 3 types of trusses in this to achieve that. But that started causing issues where the end trusses became a little too deep. So as you can see, this is the height of the column, and if a person stands in here, that becomes too much. So we obviously had to look for a different strategy rather than a simple beam that is based on a span depth ratio. There's also a high member concentration at one node, which becomes very difficult to fabricate to have so many elements come together. And it wasn't an efficient use of material as well. So this came to the final evolution where, of course, we came to this much more streamlined form where the complexity of the trusses also grew, and the end spanning system also got changed, where it was more of a cantilever kind of a truss which is anchored back into all these uh, all the lacing that happens behind. So on a broad scale, this is what happens in purely in terms of form. But the way this got evolved was with a lot of parametrics and experimentation. So as you can see, the first column which we get starts creating different kind of complexities for the start. For the start of every code, where we have parasol profiles which are divided as per the nodes, and then we start making lacings to create this. We create an essential surface on which it will be projected so that we get the 3D form. And the fourth one is how you can see how the projection happens. So this relationship of creating the pattern on the ground and then projecting on the surface continues, but we start getting more and more complexity as all these things happen, where because then we need to start discriminating of because of the spans, because if it goes more than 8 meters, like for the ones which are symmetric spans which are lesser, a simple truss could do. But as we start going to larger spans, we need to make sure that that is taken care of. So there needs to be an evaluation criteria that comes in that sets that, okay, the lacing starts from a smaller point, and then we know where the end is, because when you're working with a parametric system as such, it doesn't really understand. Everything has to be fed into that. So a super specificity is required to achieve these kind of results. And so then the process goes on where, of course, we start feeding in patterns in terms to create different patterns of lacing, where we need a few members to be dropped in the middle. And then, of course, surface creation also starts becoming more and more refined, where initially it was just a sweep created along these two lines, but then we start moving to creating a rise, then it starts creating a skew. So we need to make two surfaces, where one surface is created which ensures that everything is already on one plane, and then bulge it even more to make sure that no skewing or disfiguration of members is happening. And so so then these are the highlights of each step that come into this point, where the code starts evolving. This is what I just explained to you. And so then it's much easier to keep this track in a flowchart, where you can see how all of these starts inputting each other. And this is a much simpler version of what actually happens on the Grasshopper canvas while the scripting is going on. So by the time we came to the second one, we needed to establish a datum point over here and evaluate which spans were going more than 8 meters so that they could have a special kind of truss. So basically, the flowcharts also start creating more and more complexity. And then we can create clusters which get repeated and which get used in different ways. So by the time we come to the third one, we realize that the skew needs to be altered. So we start looking at more symmetric patterns, which involves leaving out a few nodes at the top. And with that, so as you can see in the second image, that there are some edges, some space on the curve which is not filled up because the lacing had to be more symmetric. And this starts evolving into, so the second pattern also needs to be broken down to create types of trusses. So all more evaluation criteria come in at this point of time, where we see the skew and we say this, and then we say, okay, then we need three types of trusses which are based on the kind of distance and the spans that they are doing. So this became the final thing where we needed to eliminate certain lacing, and then based on where the pattern breaks, it starts looking at different types of truss with more intersections. So if you can see the first truss, which is just a simple boosting truss, which is intersects at one point. But then the second one starts intersecting at 3 points, and then you have three members which are intersecting each other, which creates a much more rigider and a sturdier kind of a configuration. And then the third one, where we couldn't deal with that much depth at the end, becomes anchored into the second one. So the rigidity of that starts to play on this. So a lot of interplay starts getting created, a lot of ties starts coming in, and a whole mesh kind of starts creating in the structure. So the code also starts growing, where the ones which you see on the gray are more clusters which were developed in the previous part of it. So now there is a lot of data handling that is required for a process like this, where if you can see the blue parts, which are more geometric operations, they are also marked purple in the script over here. And then you have got these greens, which are basically your code for logic. So that tell you what kind of pattern, because even though we have same number of nodes, once you start making it more symmetrical and certain nodes get left out, you have got different numbers. So the program can't really understand or take those decisions on its own. And so everything starts need to be fed to it. So there is an evaluation, there is data sorting, there is data logic, and then finally creation of geometry. So this was the final product where the 13 gaps of likeliness were filled with the same logic, but different geometric configurations. And this is the final roof that we get, where there is a lot of continuity also that comes in. This is great. I mean, all of this is done. Everybody is happy. All design criteria are met. But how do you process this to state? Because it's not a simple structure that just can be drawn. And now with the model created, everything needs to revolve around that itself. So again, in a simplistic typical workflow would be you make an architectural working drawing, which helps with the structural analysis, which goes to the structural drawing, and then towards fabrication and assembly. But so last three steps of the process are pretty much the same. But instead of an architectural working drawing, we have a design 3D model. So what do you do? How do you make drawings for something like this? So we have this entire kundali of this whole roof, which is put in the kind of script. We have it sorted because the program demands you work in that kind of a way. So we have it sorted as per each bay, as per each truss, as the top members, middle members, bottom members, all of this is there. And so then we think what kind of working drawings are best suited to convey these kind of details. So the result which we come to is this kind of a thing, is that there are plans, then there is an exploded axle which conveys the design for assembly, and then there are truss elevations which tell you how to make. But to make 13 of these drawings and to make it manually just takes a lot more time, a lot more effort. And then again, if certain revisions come in because of conditions on site and all, it becomes a very tedious process. So what we decided to do was to leverage the code which existed and put a lot more code into this. So while the first top part which you were seeing was just generation of the form, the bottom part of it, almost the three-fourth part of it, is only used for making drawings. So this code started generating sheets for us. I would like to point out that Komal Agarwal from the 5th year was the intern on this, and she contributed heavily. Like all of this part was scripted by her. And we get this working drawings where we have three layouts and three layers, where you have top, middle, and a bottom plan. And then you have three types of trusses that come in after that, where you have an X truss, which is this part, the Y, which is the center one, and the Z, which is the end one, which ties back into the Z. So with this classifications happening of three layers of top, middle, bottom, and three types of trusses, we start sorting them. So the code starts to actually pick out the model and sort it into parts. So it would be actually like a physical process where you take something and then dismantle it, put it on a paper and start dimensioning. This is literally what the software did for us. So you start moving toward this, where obviously because you start arranging it in a Cartesian system, it starts giving you this. And then of course, so what becomes interesting is that there is a certain grid that gets generated. So meaning has to be assigned to that. So with the grid created, this is elevation along X15, and then you have to arrange all three layers together and start dimensioning them. So this starts getting you closer to a fabrication drawing, and this is what the fabrication drawing at the end looks like. So the workflow allows us to move from the creation of form finding, analysis. Analysis didn't really happen on this software, but it contributed to getting the input file for that. And then finally moving towards representation to show that that instead of making drawings manually and all of that, the software itself enables you to finish everything in workflow. So this is what we were looking at. The second part of it, the third part of what I was talking about the resolution. And the second part of the project is what I'll be showing right now, where this is a block. So I've explained the top part of it, of how the parasols and the roofscape was managed, but the rest of the building started functioning as one. So as you can see, there is the superstructure is in steel, the substructure is in concrete. So there is a corridor happening at the first floor level. And then there is a basement that goes along the corridor for services. And then you have smaller buildings which plug into the corridor at each point. All of them, all of this is modular construction. So the type, the spans, the foundations start becoming very, very similar for this. So this is the structure of the module where it gets attached to the trench over here. And then you can see the columns and the floor that is created. So we have a plinth level plan, and the kind of modules, there's a single module, there are some modules which are merged together. There are smaller modules which use similar kind of grids to the square ones, and that is how this is created. The footing and the foundation starts happening in this way, where we have a trench, and then which becomes a strip footing, and then smaller isolated footings on the side. We come to the superstructure part of it, where we have corridor capitals all happening in steel. Um, then the modules get joined to that, and the roofs of it. So you can see the similarity that and the repetition that is happening within this plan. So I mean, if you create one, you've essentially created everything else. But the way it joins to the main structure, the precision that is required, the alignments that are required starts varying with each instance. So we again put this on Grasshopper, and this becomes the input where we just input a bunch of center lines and profiles to start generating that. So this was a whole uh, canvas of code that was created where why is this important to show is that you can see the amount of wires that are getting interlinked, which also means that that is the amount of interlinking between the structure. So you have this corridor and then the module which is plugged into it, which has to be made sure that it sits right at the edge of it. And then the parasols are sitting on the corridor, which is sitting on the trench, which needs to be aligned perfectly. So all the work that starts happening in this doesn't happen like you don't make a 3D model and keep it at the side and start drafting separately. But the model that gets generated is the one which is going to lead to the final creation on site. So all the interlinking starts coming together, and this is where we get all the inputs. So you can see the longer ones are for the supports of the parasol, the curved one are the parasol roofs, and the trench, and then smaller center lines that happen on the side. So the advantage is having repetition and divisions over here. So there is a lot of modularity. One is that there is internal modularity. There are three types of center line inputs determining column locations on each center line. So as you can see in the first one, each center line would indicate a position of a column. And then the second one is external modularity, where center lines bunched together can be moved as an entire module. So if you grab four center lines together and just manually move them, because those center lines are linked with a certain script, the whole building will start moving. So that flexibility comes in very handy while making iterations and updating with the architectural intent of it. So as you can see the development of the grid lines leading to the form of it. So the first one is then the question becomes like, how do you translate meaning to logic and or logic to meaning in this case, where you have these lines which really don't mean anything to the computer. They mean a lot to you because you've seen the plan. But how do you start discriminating between them and saying, yes, these four lines belong to module A and the next seven belong to module B? So you can see some of the clusters which I've created here, where we start where we start creating meaning in architectural terms of what is actually data. So this shows the number of center lines which are over here, and then the way they should intersect, and the columns, number of columns that they should have. And then we divide them as per which module that they belong to. So this division starts bifurcating the data as per the architectural modules over here. But this becomes the overall logic where you have a certain data which can mean anything, but then you start sorting it into branches so that you can work on it effectively. The second one becomes about this, like, yes, these points are generated based on the lines and the intersections which we have, and the input which we have given eliminates columns in between over there and eliminates a column on the corner So this is what we start identifying those lines with. That line number 2 would mean that it only has 2 columns. Line number 0 would mean it only has 3 columns. Line number 1 would mean it has 4 columns. So so the working starts happening in this way, where all the components start getting used to classify this. So the ones which you see in green are the ones where we see proximity to the trench, because they will start becoming foundations that will get merged with the trench foundations, and the other ones will be separate. So as you can see in the render over here, these trench columns start becoming separate, and the independent modules start becoming as combined footings together. So this also starts, we could also leverage the contour surface which was given, and based on the bearing capacity and the recommendations by the geotechnical engineer, we could create foundations to the desired depth. So all the pattern that you can see on the right helps us cluster foundations together so that workability on site is easier. And the panel on the right will give you an idea about how each variation comes with the cluster of the foundations that it belongs to. So the last part of this is real-time feedback, which comes for resolution. Is that we see this plan, and then there are certain capitals which come in, but we need to put expansion joints and other things that make a building workable. So then there are a certain set of rules which come in, like expansion joint alignment can't be more than they can't be more than 45 meters apart. They have to be at the minimum width of the building, because if you put it through the entire width, then the whole it's almost like cutting the building into 2 parts, and that doesn't work well with the structural integrity, because suddenly you have a gap between spans and you need to add a lot more columns, which doesn't really work. So we start making these kind of things where, like, all those of you who may have used vernier calipers would know that there is a large scale tuning, and then there is a small scale tuning that comes for it. So we applied the same logic to it, that we initially placed the expansion joints at certain distances, and then we started fine tuning them so that we could get them in perfect alignment. As you can see, the first one where it needs to pass through a building, but getting that exact position and everything along with it becomes much more challenging. So because everything is put on the code, the joists, the purlins within it also start adjusting. So if you can see C1 and C2 over here, the small capitals which also start moving along with their movement, because it has been fed into the code. The joists and the purlins start realigning themselves based on the logic. So you can put the whole building down and then start working with fine tuning. So that becomes a very distinct advantage of this. That concludes my presentation. I think we can move to the next part of it.
Thank you, Jaideep and Varun, for this presentation. Now, I'd like to call the discussant for today, who's Komal, so she can take over.
Hi, can you hear me?
Yes, we can hear you.
Yes.
Okay. So both the presentations were lovely, and I have one common question for both of you, and I'll get into the specific questions later. But this is not entirely related to what you presented today, Varun. But since I have been going through your work and have seen that you have worked with computation as well, and since both and one thing that always comes about as a discussion in our studio, especially after any presentation on computation, is that design is something that is so inherently subjective. At how do you translate something that's so subjective into something objectified into objectified parameters and then design with it? So there are always two groups that form. One which is extremely pro computational design and tends to promote computational design to an extent that they think that architects are going to be obsolete and we are essentially going to become programmers. And then there's the second that are extremely skeptical. So I think I just want to understand what your opinions are on this and where do you stand?
Jaideep, do you want to go first? I think you are the you should go first, and then I'll kind of.
Um, I think it depends on how do you place the project, because however subjective design might be, it needs to, if one is thinking of manifesting it into reality, that is building it, the part where it stays subjective and subject to change also is very small in the design process. After you start incorporating a lot of other consultants, other people, and other realities of buildability, all of those subjective things start um, to be frozen at a certain time. So yes, like the part where all of the project is on your drawing board will be a small part where you can take certain decisions. But then after that, that needs to move to certain specific criteria, because that's how you can engineer the whole building as it is. So yeah, I mean, of course, as I mentioned in the beginning of the presentation, computation and parametrics have certain advantages which will lead to a certain kind of a result. And if the project becomes more repetitive in terms of logic, not necessarily in terms of its form, it is possible to adapt it to that situation. But there could be projects which do not, which are not logical, and the designer is whimsical enough to treat each part differently. So that would be very tedious in implementation from a computational perspective. So I don't think, if at the end of the day, all of these are tools. So we don't need to necessarily say that this is the only path we go down on. It can stay in its own domain, and we can use them where it feels necessary.
The kind of so I kind of used computational differently. My partner on this project, Matt, and I. So the way we dealt with it was because we were interested in sort of these objects coming together. We started off with very analog techniques like the hot wire cutter that we have at KRVIA. We have a similar one at our school. But the primary reason for using a wire cutter to use them to create joints that kind of came together and sort of misaligned was because a wire cutter is always a straight line. And so when you make things that are not really straight lines and that are really complex, what helps you is that when the straight line creates an object like this, computation helps you solve that really easily. Um, and so the way we used computation was purely for resolution and not for form finding. Um, I'm personally, I like thinking about computation as something that is more resolution oriented, because in terms of form finding, it kind of starts to get a little repetitive and mundane over a period of time for me.
Okay. The next question I have is for Varun. So it goes. Usually, when we conceptualize design, we actually start with a very anthropocentric approach, where the people using them or the program takes precedence. And what follows, especially in higher years of education, when we have the burden of multiple things to take care of on us. It is very rationale driven. It is in like whenever we have to go back to something, the social aspect or the people who are going to be inhabiting it form the are given precedence. However, in your case, when the object was taken as a starting point, uh, the process turned out to be very different. And you have highlighted ways of design where the human is slightly decentered and how this helps other factors. But uh, but basically, what I'm trying to ask is what essentially becomes your starting point. If you have to even come up with an object, how do you even start to move forward with that?
So the way the firstly the reason about moving away from anthropocentrism to sort of object centric ideas was to in was to sort of react to the essential change that we are going through right now. Climate change has become very real today, and a human-centric, consumer-centric approach of design has has kind of led to this crisis per se. So the lack of anthropocentrism comes from there. Now there are two ways of dealing with this process, and that's how I deal with it at least. One is on a very aesthetic level, because aesthetics and what you see around you, the world building shapes reality for you. So that aspect is a lot of my presentation was about those techniques that we use for the creation of form. And the other aspect is, of course, very highly landscape, technical landscape oriented ideas that come in, which are what, which are sort of the things that the trees do, or the sort of connections that we establish between when a tree sort of sits next to a lake, on a shallow lake. How does the branch of the tree react to how will a bird kind of sit on the tree, and they will fish, the fish that kind of are in the shallow waters during, say, the hotter times of the day. So you kind of deal with the object discourse on two extreme levels, and you have to kind of, the way I conceive projects, I deal with both at the same time. And one is very artistic, and one is kind of the technical side of it.
That's interesting. Okay, so the next question's for JD. So usually at the academic level, when we design or we work on a project, structure and its resolution comes at a later stage, and it comes at the resolution ki, okay, now we've finalized on this. This is the mass, this is where the programs are. Now we'll put columns. These are the beams. My roof will be spanned like that. But can structure itself somehow become the driving factor? It can. It surely can. But how would you suggest students who are interested to in understanding and designing purely with structural intents navigate the entire design process? Because I think even when we try to do that, we in the process somewhere get stuck. Okay, we don't even know where to go with it. So how do you think
I
we
think
should go about?
this is a question that Manjunath sir would answer better than I would, because I I don't think I can design with purely structural intents in my head by now, because it would really come down to, how much you are aware of structure, and how much can you translate and form, and how much you can identify. It just comes down to personal capacities at all times. Especially difficult in college, because you're just coming to terms with what architecture is. To get one more discipline along with that, which is a whole new degree by itself, is really challenging. So I mean, you can start pursuing your interests, which could be anything, which could be structure, which could be anything which could be integrated into architecture. But I don't think there is any way or a formula to do that. It just depends on your sensitivity towards identifying it and translating it into form, space, and structure.
Okay. Mamta?
Yes,
Yeah,
Koman.
I'd like to call Manoj right now. He might have some
Yeah, we can
questions.
open up the questions now. Yeah.
Yeah. If anyone has any questions, they can ask right now. We're open up to questions.
Manoj, would you like to unmute and ask your question, or should we read it from the chat?
I think read from the chat.
Okay, I'll just read the question. He says, Varun, is your argument about configuring object ecology and syntactical aspects of architecture, because they seem to be contradictory. One is contextual while the other is not.
That is the point at which I spoke about objects landing. And so it depends on because I'm calling it object ecologies. It depends on the it objects can objects are so there it's not that they cannot react to other objects that are within their context or that they are stuffed into. It's the fact that they need to be treated more autonomously as entities in themselves. I mean, even in the projects where objects have sort of gained complexity from their context, the context hasn't necessarily been physical, or the context hasn't been something that is already there. In the project that I mentioned, where they gained complexity from the context, it was borrowed histories that created the layers onto the objects, and the histories were borrowed from that place. So these were maps and drawings that were created way before these objects were placed there. So it was using the past to kind of project into the future, and the complexity was gained from an abstract realm, not from the immediate context of the objects.
Thanks, Varun.
Hi, Varun and Jaideep.
Hello.
Great to listen to you all. And as faculty, it's always nice to hear what you all are doing in life. I just have one question to both of you. I mean, it need not be too elaborate, but how did the question is, how did the pedagogy in KRVI shape the direction of your thinking to where you are right now? I mean, this is open to both of you all. Because it'll be interesting. There are lots of students out here, and for us faculty, I mean, if we need to tweak it a little bit, it'll be quite interesting. I mean, any of you can go. And fantastic presentations to both of you. You are very articulate in what you all are saying. So yeah.
You want to go ahead because you're.
So there are two projects that I showed. One was my third year project, which I did with Vandana, and which was the project in which I tried to explain stuffing. The idea of a object-oriented discourse not only started from my home and my upbringing, but it was also sort of fed into by these really amazing people at KRVI who sort of fostered my growth. And it was then again taken ahead in my thesis when I did it with Manoj sir. It was then purely about giving those objects the complexity and making them land onto a ground. And of course, I had not articulated it as an object-oriented worldview by then, which kind of later came together as I read object-oriented ontology and after leaving KRVI. But definitely, like, the remnants were encouraged and grown, and the diversity of views was always appreciated in our times.
I think the pursuit that I have been after graduating is basically going after things that I felt were insufficient in the knowledge or the skill set which I had, and that is what I tried to explore in professional life. So I think college gave a fantastic exposure in terms of different contexts. I mean, we had study tours all over the place, very different contexts. There was a lot of understanding and exposure to design languages, design concepts, translating them into form. But so that felt quite sufficient. That yes, I mean, there is a lot of confidence. I mean, we were confident right from third year onwards to start doing houses on our own. And of course, in hindsight, all of it was overconfidence because we didn't know what we didn't know. But so moving to other projects like interiors, maybe a little bit of urban design also, and then structure design, is that when all of those things which are there, that yes, you feel confident enough to do a building in a certain language or to put it in a certain way, then I think the next question that came is, how can you do more with what you have? And then there start coming a need for collaboration, for external knowledge that comes in. So if I would say that KRVIA left me with a very strong foundation in terms of being an architect and putting buildings on paper in terms of the way the discourse is shaped today, I just felt like there was a larger need to be more technically proficient in whatever I needed to achieve. So in terms of construction system, of course, a lot of it is not, most of it is not possible to achieve in college with the discourse being so vast. So it was basically moving to places where I found that yes, this is something which is outside, and I would like that in my repertoire.
So, like, honestly, KRVI has a fantastic network which gets you to these places because I wouldn't have ended up with Zamir had I not been directed there. And had people at KRVI not seen me pursue the projects like that. And so I just grew in my own discourse just because KRVI was my starting point.
Thanks a lot. All the best.
Thank you.
Do we have any more questions? Oh, hi, Avni, you're on board. Great.
Yeah. Hi. Are there any more questions from the audience? You can write them in the chat as well as raise your hand. We have Manoj's question. Manoj, if you're here in the meeting, you can ask.
That's done already. Avni, that's done.
Okay. Sorry.
So I have a question, Varun and Jaideep, especially I think when Varun spoke about his thesis project. And I would like to know, for the benefit of the fifth years and the next batch of students, as to what are the kind of challenges you face when you articulate your final aim or final design in this particular way, especially when you have to deal with a lot of university kind of requirements and rigor and all of that. So how were you able to negotiate with all of that, Varun, first, and then Jaideep?
So the negotiation was extremely hard, to be honest, because the project was designed to be starting in a more theoretical realm and then ending into a final project, which was more of a demonstration of the theoretical premise. And the university has a little bit of an absurd set of requirements where you need to explore it structurally, that it has to be a tick mark box. And kind of in my third year project was complex enough to demonstrate that structurally I can deal with complexity. And to kind of expect that and to expect services and to expect other things at a university level is a little absurd when you have already kind of tested it in the third year. So I feel like that kind of needs updating. But the way I dealt with that was to try and integrate it with the framework as much as possible. Because, like, for example, on the object project, the grids were shifting, so I kind of used those grids to demonstrate a certain level of structural competence. But it did not help. But those are the challenges you take for growth.
So, is that question applicable for me as well?
Yes, Jaideep, because you've probably positioned yourself differently, right, from Varun, especially
Right.
with your thesis project. So what's your take on this?
Can you come at it again? I'm sorry.
Yeah, so I'm talking about the rigor that the university expects you to go through. And when you want to take this strong theoretical kind of position,
Right.
how do you deal with negotiating all of that? Like Varun put it, it was very challenging for him. So how did you find it?
Um, of course, I haven't done a master's, so the thesis that I can talk about was college Kamla Raheja itself, and that was really difficult for me personally because there was a bit of clarity also that I was looking at where I was getting interested in other things, and I didn't know how to channel all of that. So like curiosity start coming up ever since since college itself, where you suddenly get more interested in something that perhaps doesn't occur, cannot happen in an academic space also. And I also faced a lot of conflict personally at that level. But I mean, I guess that is how academia is structured, that you can it just needs coming to terms with that certain things can happen in college and certain things you just need to have patience for, because like any other art or a field like this, there is a lot to be explored and you can't do it right away. So one of the things that it taught me was patience. I mean, college does enough to instill rigor, which has helped me tremendously. I mean, all the places where I work, the rigor is one thing which I took away from KRVIA, which has served me really, really well about meeting this. So when it comes to working in a place like this, the learning, I mean, essentially you come to this place to learn, to see how the other side functions and how collaborations can occur. And I think that rigor helps tremendously, where you have to start to learn by doing, so there's no one giving you theory or anything. You just do it first, and then you look back at it and just think what you've done. So if you do not have that rigor, then it becomes really difficult to actually move ahead in a setup as such.
Yeah, great, thanks. That was wonderful. Any more questions, Avni?
No, I don't think there are any more questions.
So I think that was fantastic, and it has been, I think, a great, I don't know, great initiative where Manoj, kind of thought of bringing in alumni to speak to the students. That kind encourages them, I guess, to move forward with their design ideas, with their kind of direction to life later on post graduation. So I think that was great of him. So thank you, both of you.
Yes. Thank you so much for inviting us. I mean, I don't know if I expressed my gratitude at the beginning of the presentation. I was a little caught up with screen sharing and everything. But this was this was a great honor to be on this platform where we have seen so many other people that we look up to come and present, and for giving us this opportunity and the honor of talking to students like this.
Right.
I mean,
Great.
thanks a lot. I couldn't thank enough. The same thing applies to me. Actually, I wanted to say the same thing.
Right.
And
This is going to be encouraging for the students now, the fifth years and the fifth years to come, to pursue, their let's say their complete design ideas which they've grown with through the trajectory of 5 years, and take that forward and not get discouraged by the checkpoints like Varun said. So yeah, it was great. Thanks a lot.
thank you so much.
Bye.
Do you have any email IDs to which we can reach you if we have any questions?
I could share the email IDs with Mamta, if that's okay.
Yeah, that will work.
Sure. We'll share our email IDs. You can get in touch with us.
Yes.
All right.
Thank you
Okay.
so
Thank you.
much.
So much.
Thank you so much.